like to show you how to analyze clock jitter using unique features of the Agilent 53230A counter, statistics and histogram. Let's move to the front panel. The instrument is set up for time interval measurements, taking 10,000 readings. Initially, I have a clock signal coming in with noise, random noise. So I'm going to first of all use the statistics function to show how you can use numerical analysis to figure out what's going on. I trigger the instrument. I come up with a peak-to-peak value and a standard deviation that has a relationship of about 6 to 8 to 1. That's indicative of random noise. If I change the signal source to a sine wave, clear the measurements, trigger the readings again, now the relationship between peak to peak and standard deviation is almost 3 to 1. Then change the source one more time to a square wave, clear the measurements, and trigger the readings. Now the relationship is approximately 2 to 1, indicating square wave noise. That's great and it's very useful information. But what if I want to see that graphically? You can use the graphics function, the histogram. You can configure the histogram using the mins and the maxes already made from the previous measurements, and then trigger the instrument, and you can see there's a bimodal distribution indicating square wave noise. If I change that noise to sine wave, clear the measurements, and trigger, now the indication is more of a sinusoidal noise source. And then finally, if I go back to Gaussian noise or random noise, clear the measurements and take the readings, now I get a random distribution. And finally, I'd like to point out that you can move back and forth between the numeric and the graphics keys, so you can compare the results of the statistics and the histogram. So using the numerical analysis of statistics or the histogram graphics analysis are powerful tools available for the 53230A counter.